So this is going to be chapter 12, part 1 on valence bond theory. Valence bond theory is actually a continuation of the Vesper diagrams that we were talking about in the last chapter, in chapter 10. And so the idea here is with valence bond theory, if you had carbon CH4, okay, what you would draw for the Vesper diagram is carbon, the hydrogen up, hydrogen to the side, and a hydrogen forward and a hydrogen back as well. In this model, each one of these bonds between carbon and hydrogen are the same length, although they are different orientations, and they are all evenly spaced. Okay? The problem here is if you were looking at just regular carbon, okay, and the electronic configuration, you would have 1s, 1s2, 2s2, and then 2p2, okay? So this would be the electronic configuration. The book uses these circles instead of boxes, but they're the same thing, okay? So this would be what carbon looks like, okay? And so you're looking at it and going, if I'm coming in with my hydrogens, okay, I can come in and make bond to the if hydrogen comes in with its electron, put one there, put one in that box, and then, of course, two more in this box, okay? But the problem is they would not be really the same orientation as what we see in this model here, okay? So the author says that there's another model that was proposed, and wherein you take one of these electrons here and you move it into this orbital here. So you end up having 4 orbitals with 1 electron in each. And so you can add your 4 hydrogens, one here, one here, one here, and one here. Okay, that seems fairly good of a model, right? You have places where you can put the hydrogens, everything looks good. The problem is, if you think about it, 2s is like this, okay? So if it makes and hydrogen's 1 electron is in the 1s, so, you know, hydrogen comes in, this is your carbon, that's your first bond. Then the the 2p has px, py, and pz. So if you have your pz, you know, it's making a bond with your hydrogen. Then you have your px, and it's making a bond with the hydrogen, and you have your pz, and it's making a bond with the hydrogen. This looks nothing like this model, right? Okay. In fact, this model doesn't fit well with what we're seeing in the Vesper diagram. So this is why we need this new idea of what we call hybrid orbitals. Okay. So we're going to go through and talk about what exactly are hybrid orbitals. And so really, hybrid orbitals are where you take orbitals and you mix them, okay? And with the carbon atom, a hybridized model is the best because if you take your 2s and your 2p, you're moving one of these electrons here, okay, up to here. So you have 4 electrons here. And what you're doing is you're taking all of these hybrid orbitals and you're making them 4 orbitals at the same energy. We call it sp3. Notice this terminology here. sp3 meaning you're taking 1 of the 2s orbitals, okay? 1 of the 2s orbitals, and you're taking 3 of the 2p orbitals, 2px, 2py, 2pz, and you're mixing them together. You should come out with 4 new orbitals, which looks like, well, we're going to talk about what it looks like in just a second, but you have 4 new orbitals and they're all at the same energy, okay? The fact that they're at the same energy means that the bond length should be fairly similar, okay? Now let's talk about what it looks like when you mix these orbitals together, okay? You have an s orbital that looks like this, and then a bunch of orbitals that look like this. This is the px, py, and pz, okay? You're going to get out 4 new orbitals, okay? And they're going to be in 4 different directions, right? One will look like this, okay? One will look like this. This should be more round, okay? One that looks like this, right? And another one that comes kind of out like this, right? So if you have a bunch of these different things, there's a little bit of an S character from the round side, but it does look like a dumbbell with two lobes and a node in the center. And so if you put it on the x-axis, it kind of looks something like this, and it matches the tetrahedral orientation of, you know, one orbital here, one orbital here, one orbital here, and one orbital here. And if you bring in your hydrogens, then it looks like this model right here. Okay. The nice thing is, remember, they're all at the same energy, and this situation, the blue arrows are the hydrogens. Okay, and so hydrogen comes in with one each, or 4 hydrogens. So that you have an octet, which is what we'd have in the valence bond theory. Okay. So really, what are hybrid orbitals? And we know this word hybrid from science, in life science. There are hybridizations of other things. For example, if you have a polar bear and a grizzly bear, if they mate, then they make what we call a growler bear, and this is a real thing. And so the growler bear looks somewhat like a polar bear and somewhat like a grizzly bear. So there are characteristics of both in the growler bear. In the same way, if you have a round s orbital, and then you have a lot of these dumbbell looking, like with the 2 lobes, p orbitals, you're going to get orbitals that look stretched and elongated, but still round, right? So that it has some characteristics of the s orbital and some characteristics of the p orbital, okay? The book draws it like this. Some other people, they draw them like this, where it's like this, and then a little lobe here, right? Like this, and then a little lobe here. And then you have one coming forward, and then a little lobe, and then one kind of going back, and then a little lobe. Okay, and so the book obviously has not drawn the little other lobe on the other side, the tiny little lobe. And this matches very well with our, right, our C, our forward, and our back situation with the CH4s. So this model actually fits very well with the templates we were looking at last week. It is very important to remember the number of orbitals you mix together must be the number of orbitals you get out afterwards. So if you take 1s and then 3 p's and mix them together, 1 plus 3 is equal to 4. So you need to get out 4 sp3 orbitals. Okay. Each orbital is called sp3, so you're going to have sp3, 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 sp3. Okay, and they're all called sp3. Okay. All right. So the definition of a hybrid orbital, therefore, is an orbital used to describe bonding that are obtained by taking combinations of atomic orbitals. In this chapter, we're looking at combining the s and the p of the isolated atoms. Okay, and it's not just, so we did look at S1s and 3p's. Okay, there are other ones. For example, if you have, and this is your 1s, and we're never going to hybridize the 1s because the 1s is a non-bonding, non-valence electron. Okay, so we have our 2s and our 2p. Okay, if I took, instead of 3 p's, I only took 2 of them, okay, and I hybridized, okay, then I should get out, again, my 1s remains unchanged, it's not hybridized, and it is not involved in bonding. Then I get out, and remember, the number I mix is the number I get out. So if I mix 1s and 2 p's, I should get 3 sp2. The 2 meaning that I picked 2 sp orbitals instead of 3. Notice I have one leftover p, so I'm just going to leave it. It's a little bit higher in energy, and I'm going to leave it. It's my 2p orbital. Okay, so these are the ones that I hybridized, and this is my leftover. Okay, leftover, untouched, whatever you want to call it. Okay, and we can do that again if, let's say, we take our 1s, which we're not going to touch, 2s, and then our 2p. Okay, let's say instead of grabbing 2p's or 3p's, okay, let's grab 1p and 1s. So we're only going to take and hybridize one of the two s's and one of the two p's. Okay. Remember again, if we go in with two orbitals, we're going to come out with two orbitals. Okay. And we're going to call these two orbitals sp. You can think sp1 because they're really going to grab one orbital of p, but we just leave off the 1 and just write sp. Okay. We do have two leftover 2p orbitals, which we haven't used. So those are this is the new hybridized orbitals, okay? But we also have, notice here, 2p that's left over, and we're just gonna leave them there. They haven't been touched, and they do come in useful to make certain kinds of bonds. Oops, 2p, okay? So this is what we call an sp2 hybridization. This is called sp hybridization, and if we scroll up, this kind of hybridization is called sp3 hybridization, which we have here, okay? And so we're gonna get into that a little bit more and how to draw these pictures in just a second, okay? So why do we need the three kinds, the sp, the sp2, and the sp3, okay? It is because these hybrid orbitals have been assigned to certain geometric arrangements, okay? So if you have linear, okay, you have an sp hybrid orbital. If you have trigonoplanar, you have sp2, and if you have tetrahedral, you have sp3, okay? And of course, there are two others, trigonal bipyramidal is sp3d, and octahedral is sp3d2, okay? Obviously, d and d2 just means that in addition to the 3p orbitals, we're also going to include in our hybridization 1d or 2d, depending on if you have trigonal bipyramidal or octahedral, okay? That is nice because in the SP, we have a linear arrangement of 120, and SP3, trigonoplanar, sorry, SP2, a trigonoplanar of the 3 SP2 orbitals, and so on and so forth, okay? Think about it. If you have SP2, really you're going to have, you went in with one S and two P's, so you add those together, so you're going to get out 3 SP2s. So this is SP2, SP2, and SP2. And you need 3 because you need trigonoplanar, right? So you're going to have some atom in the center, and SP2, SP2, and SP2. These are all SP2. And notice in this arrangement, you do get trigonoplanar, right? And SP is the same, right? If you have one S and one P, you're going to get out two SP orbitals, okay? And so you're going to have SP and SP, okay? And I'm going to stop drawing these little tiny nodes because it makes things a little bit more confusing. I'm just going to draw the big lobe. But notice here you have linear, which is what you see up here. Okay, so they have rules, and we're going to go over these rules in just a second, where it says you should write the Lewis dot structure, then from the Lewis dot structure, predict the Vesper model, and then from the Vesper model, you get the geometric arrangement, and then from the geometric arrangement, you're going to use this table to decide SP, SP2, SP3, and then from there, you can hybridize, okay? And we're going to go through that step by step, okay? So let's look at this example here of C2H4, okay? The Lewis dot structure is as drawn here with a double bond in between, okay? Now, if we're looking at this carbon here, okay, it would be AX3 because there are 3 atoms attached, okay? So if we're looking at this, AX3 would be trigonoplanar, or geometric arrangement would be trigonoplanar. Okay, and again, you need to have your Vesper table out in front of you to figure that out. Okay, trigonoplanar would give you SP2. Okay, so the Lewis dot structure, the Vesper model gives you the AXE, whatever that you have, the formula, and then you have your geometric arrangement, which will get you the hybridization, in this case, SP2. This tells you that you need to take 2 P's and 1 S, and I've selected that here, 2p and 1s, and you're going to hybridize and get, and remember you have one orbital here, 2, 3 orbitals. So you should get out 3 orbitals, and each of them is sp2. Okay? Then you, of course, have the leftover 2p, which we just drew right there. Okay? With carbon, remember that there are 6 electrons, 4 of which are valence. So I put them in there, 1, 2, 3, 4, 5, 6. And when you fill them out, you should again fill them out according to Aufbau's principle, 1, 2, 3, 4, 5, 6. Okay? Now notice you have 3 sp2s. Okay? So it's going to be, and both of these carbons are the same. They're all X3, right? So carbon, and you've got your sp2, your sp2, and your sp2. The other carbon, same thing, right? sp2, sp2, and sp2. Okay? So if you put in your electrons, there are 3 electrons, right? 1, 2, 3. I'm going to pair them up, and remember, if you're making a bond, it should be up then down. So this is a bond. This is 1 electron and 1 electron, right? Each carbon has 4 valence electrons, okay? And of course, your hydrogen will come in with its electron. I'm going to put it facing downwards since the other one is facing upwards. Okay, so it looks good so far. I've got my sigma bonds. Those are the single bonds between the carbon-carbon, the carbon-hydrogens, etc. Okay, but there is a double bond here. So really, where are the other 2 electrons sitting out in the 2p? Where do they go? Well, we should draw those in as well. Okay, so I'm going to draw the 2p's, and remember the 2p's are up, down. There are 2 lobes. Okay, okay, and there's 1 electron here. There's 1 electron here. This makes another bond right here. Okay, and this bond is called a pi bond because it has an electron distribution above and below the bond axis. Okay, so really this is what the pi bond looks like. Okay, above and below. Okay, it's as if you were bringing your 2 p orbitals close together. The bonding would be here and here. There would be no electron density between the 2 atoms in terms of right here. Okay, there's nothing there. Okay, so really these are your sigma bonds. And then there is your pi bond, right? So if you wanted to label it in your orbital picture, this would be your pi bond. This would be your sigma, your sigma, your sigma, and your sigma. Okay, so in this particular model, you have, and one more here, between here. It's 5 sigma bonds and 1 pi bond. Okay, so you can do that for not only a double bond, but you can do that for a triple bond as well. And this is C2H2. Okay, C2H2 has a triple bond, and so if you're looking at this carbon here or this carbon here, choose one. Okay, let's choose this one here. It would be AX, and there are 2 atoms attached. Okay, if you look at the other one, it would also be AX2 because there are 2 atoms attached. So each of these carbons is what we call linear in the geometric arrangement because it's AX2, so it should be sp hybridized. Sp hybridized means I should grab one of the 2s and one of the 2p orbitals to get sp, which is exactly what we've done here. Okay, and so really we should end up with 2 sp orbitals. We do have 2 leftover p orbitals here, and they are happily sitting out right there. Okay, so if we're looking at the valence electrons, okay, and we're drawing it out in terms of the hybrid orbitals, we have an sp and then an sp. Okay, and that's your carbon in the center. And I have another carbon here, and you're going to have your sp and your sp. When I stop drawing the little lobes, it's totally fine. And so really you have an electron here, and an electron here, an electron here, and an electron here. Okay, so 4 electrons, 2 from each of the carbons. In addition, each carbon has 2 2p's. I'll draw these in blue. Okay, there's one like this, and it has an electron. The other carbon has the same thing, 1 electron. Okay, and this is going to make your pi bond. There is another pi bond, p orbital, and so it's going to go front to back, and again it has 1 electron, and so this is another pi bond. Okay, and then of course you have your 2 hydrogens. Your 2 hydrogens came in with its 1 electron. Okay, and so this is what it looks like when you draw the orbital picture. Okay, the book has it broken down for you. This is your sigma bond. Oops, sigma bond. This is your sigma bond, and this is your sigma bond. Then you have 2 pi bonds, one here, up and down, and then one here, back and front. Okay, and so really, if you were labeling it on the actual structure, you have your pi, your sigma, and your sigma. Okay. So really, it would really help you, I think, to get started on the homework. Okay, and the next video will go into a little bit more about templates for the orbital diagrams. So don't yet attempt the homework on the orbital diagrams yet until you've watched the next video. Okay, but the first thing I would do, and this is going to help you on the first page of the homework, is to take the VSEPR table that you have from last week. Okay, and I would mark it up, right? Because if you think about it, the SP is linear. So really, linear is SP. So write that there. Okay, then the trigonal planar is SP2. So you write here SP2. The tetrahedral is SP3. Trigonal bipyramidal is SP3D, and SP3D2 is your octahedral. I would mark this up right now so that you have a good idea of what to do in terms of your next, when you're doing the next part of the homework. The other thing that you should know how to do is be able to look at a structural formula like I have here. Acetaminophen is a pain reliever in a lot of the over-the-counter pain relievers like Aleve. Okay, and so you should be able to look at any of these atoms and assign the hybridization. Okay, so on the homework you'll have to do this. Okay, so for example, this oxygen has 2 lone pairs and 2 bonds. So this would be AX2E2, right? It's AX2 because there are 2 atoms attached, and it's E2 because there are 2 lone pairs. So AX2E2 is here. Okay, so it would be, the geometric arrangement would be tetrahedral. And the hybridization would be sp3. Okay, let's look at another carbon atom. This carbon atom here, okay, would be AX3. Why is it AX3? Because there are 1, 2, 3 atoms attached, and AX3 would be trigonal planar in its geometric arrangement, and trigonal planar AX3 is right here. So we would say that it is sp2 in its hybridization. You will have to do this on the homework, so it's good to make sure you know how to do this. Okay, we can do one more. This nitrogen has a lone pair. Okay, so this nitrogen would be AX3E because it has, and I'll do it in a different color to differentiate, this nitrogen has 3 atoms attached. Okay, so AX3 does have a lone pair, so we have E. AX3E predicts, again, the geometric arrangement of tetrahedral. Again, we're not looking at the molecular geometry, or looking at the geometric arrangement. And so AX3E would be right here. So it would again be sp3. Okay, so this is how you should do the homework. That first page there, you should be able to draw the Lewis dot structure, and then from that determine what is the geometric arrangement and then the hybridization.